Wordle, the game that's all the rage. Hang on. Well, it was all the rage when I started writing this program in March, but hey, better late than never. Hello and welcome back to another video. Thanks to its logical nature, Wordle is a game that can be programmatically solved, or at least algorithms can help to assist a human player, which is ultimately what piqued my interest as a programmer in the first place. But upon closer inspection, you'll find that Wordle solvers are really just looking up a dictionary. It's still fun, don't get me wrong, but I just wanted more. That's why this episode isn't about Wordle, but its derivative, Nerdle. This version of the game requires you to create a meaningful mathematical equation, but otherwise plays in the same way as Wordle. So here's the story of me trying to build a tool to essentially crack Nerdle once and for all. That's computational thinking right there. Why take a few minutes out of every day to solve it when you can write code for like an entire week and solve it for good? For whatever reason, I also decided to apply a bunch of software engineering techniques along the way as I developed this application. So here's a chance for you to take a peek at the so-called standard software engineering process in solving a problem. So heads up, today's video is going to be more focused on the software engineering aspect as opposed to the algorithm side of things. My goal today is to define a lot of software engineering terms and put them in a practical context so you can understand them. The actual algorithms aren't all that hard, but if you're interested in hearing more in-depth explanations on it, let me know in the comments below. Let's start with the results because a lot of you think I talk too much. Here's the application in question. It is a fully web-based project with a graphical interface. Nerdle is all about guessing an equation, right? So long story short, you dial in the digits and operators, henceforth known as glyphs, and whatever else you know about the equation of the day, and then click guess. A set of possible candidates appear at the bottom of the screen, sorted in some vague order of priority. You will then switch over to the actual Nerdle web page, key in the solution, and get feedback. If you're not familiar with the typical Wordle feedback, just know that it works a lot like Mastermind does. If you've guessed the glyph correctly and in the right position, it's marked green. That is correct, and you don't have to worry about it anymore. Otherwise, if your guess does appear in the final answer but is in the wrong position, it is highlighted purple. Conversely, if the glyph doesn't appear anywhere, it's colored black. All this helps you narrow down the possibilities regarding which glyphs are involved and where, and the hope is that eventually you'll have enough clues to eliminate all possibilities except one, the correct answer. What my app allows you to do is to mark which digits and operators must or must not appear, according to the feedback given. Then, you'll click guess again to refine your search. This process repeats until you get the correct answer. So now that you know what the end result looks like, let's jump back to the very beginning, before all this exists, and start from scratch. At the outset, I really only knew one thing, which was the approach we could take to make guesses. The core of this is an exhaustive recursive search. Each digit or operator in the equation must be one of the symbols in the full set of possible symbols. So for each position, simply try out a certain glyph, then pass it on, and recursively guess for the next position. Keep going until you reach the end, and you'll have enumerated all the possible candidates to guess at. As you can imagine, this search gets massive. Thankfully, many optimizations are available, allowing us to prune this list of possibilities way down. They are as follows. If we already know what number is supposed to go in a certain position, we don't have to guess, obviously. We can also take feedback on board. If we know a value never appears, we don't have to try it at all, while solutions not containing must-haves can be eliminated early. And don't forget, we're guessing at equations here, so it's not really true that everything goes. Equations that aren't valid can be instantly eliminated, and these usually come from operators appearing together where they shouldn't, like minus times, for example. Of course, equations that aren't mathematically correct can be eliminated as well. While many of these sound trivial on their own, every combination eliminated really represents huge gains because all combinations that follow from it are equally invalid and thus do not need to be explored. With this basic idea in mind, I begin delving into implementation details, that is, how I would actually want to realize this project. At this point, it's all still planning, thinking of the tools and methods I would use moving ahead. I started by deciding on a platform, I love Python and have been using it an absolute ton lately. However, in this case, since I wanted a graphical user interface or GUI, I decided to go the web route. Not wanting to overcomplicate things too much, I decided to go with just vanilla HTML, CSS, and JavaScript. Now, there actually are reasons why I wanted to get more software engineering for this project instead of jumping right in. That is contrary to what I said in the opening. In order to manage complexity and at least have some confidence in the project's correctness, I decided to apply several broad software engineering methods, starting first with modularization and the MVC pattern. I wanted my code separated nicely into modules that didn't interfere with each other too much. Each module would live in its own code file, and ideally, I would minimize coupling between the modules. That is, each module shouldn't have to care or rely on how the other modules work, so that if I change a module, I wouldn't have to update everything else to match those changes. It also helps to have high cohesion in my program. That is, each module should handle one responsibility of the program in its entirety. With low coupling and high cohesion working hand in hand, my program should be built as modules that each handle one major responsibility while being blissfully unaware of anything else that's going on in the program. In order to enforce this as much as possible, I decided to apply the very popular MVC or Model View Controller pattern. The goal here is separation of concerns. The model consists of the main data structures and algorithms that power all the heavy lifting of the program. The view is its GUI, while the controller acts as the middleman between the two, taking in user input via the view and passing them through to the model. The model and the view quite literally have nothing to do with each other, thus reducing the coupling between the two. Following MVC allowed me to structure my project very early on. I ended up creating separate files for everything. The view lives across an HTML file and a CSS style sheet, while the controller and model were separate JavaScript code pages respectively. My personal habit is to start with the model first. Since the model exists and works on its own and is technically capable of solving the problem just without the fancy GUI, I like to give the model a head start. By the time we get to the GUI, we already have a largely working model. So we'll never have to test an entirely buggy system all at once, because that would be a really bad idea. And even while focusing on the model, there are things to prioritize. You see, the solver has many complex moving parts and rules to check. If you were to try and write them all at once, you run the risk of having bugs pile up and having to wade through a ton of code to find them. To mitigate this risk, the second major software engineering technique I'm using here is what is known as the top-down approach to organize everything. The entry point to this file is the generate possibilities function, which is meant to do everything. But here's the cool part, I don't have to do everything, not just yet. Instead, every rule I want to check will be implemented as a function, all of which are called by generate possibilities in turn. This allows me to determine very early on the exact flow of events, and to comprehensively set out all the rules I want the program to check. I can even add these functions before I want to actually write them if I want to. Without any implementation, these functions, which we call stubs, will return whatever appropriate value that allows the code to continue, effectively being transparent. When we do want to write them later on, we already know they'll be called at the right time and their results used properly. At this point, even though we haven't actually written any real code that goes towards solving the problem, we do already have quite a few code pages and function stubs. As we jump into the coding process, it becomes more and more important to maintain a record of what has been done so you can retrace your footsteps if it's necessary to do so. This is where revision control comes in. You've probably heard of Git, and that's what it's for. Such tools really shine when you're working in a team with other coders because they help you reconcile changes and get everyone on the same page, whether they have the same responsibilities in the project or not. For this project, I'm working on my own, but there are still many ways in which I can take advantage of Git. At its simplest, I get to work incrementally, tracking my progress as I go along. I start small, and every feature I've created and tested gets committed to the repository. You can think of every commit to be a snapshot of the current state of the project. In the future, if I ever mess something up, I can return to those earlier snapshots to see what has changed and to pinpoint the error. Later on in the project, as it becomes bigger and more mature, I can even work on different aspects of the project at the same time by creating branches in the repository. Each branch can represent one part of the project, say GUI enhancements, while another could be involved in, say, the optimization of the algorithm. When the changes are complete, they can be merged back into the main branch. And finally, one of the software engineering techniques I was most excited to apply for this project is automated testing. You see, this project in particular really needs this. Each rule used by the algorithm is complex and has many edge cases. This usually means extreme inputs that may lead to some unexpected outcomes. If my understanding about any of these rules is fuzzy or poorly defined, I could very easily miss something out, and exercising these risky cases by hand will be tedious and error-prone. With automated testing, I can create a set of tests that I can run every time to ensure that this predetermined set of expectations aren't violated. Every time I add a new feature, I'll run all the tests again. Sometimes it'll unexpectedly break a different part of the code in a way that would have been difficult to find out if I was doing just basic exploratory testing. That's why I'm glad to have used automated testing here. In this case, I'm doing unit testing with Chai and Mocha, set up such that it can be run entirely within the browser. With everything in place, I can finally begin actively developing. I begin by prioritizing the basic functionality of the program, with the goal of getting something working nice and early. I begin with only the simplest checks for validity and correctness to eliminate the most obviously bad guesses so that the search wouldn't take forever. To prevent the project from spiraling out of control, I take care to immediately implement test cases and to watch them pass before committing to revision control and moving on. The more tests, the better, and I often try to use a mix of black box and glass box methods to test my functions to boost confidence. Black box testing tests the abstract definition of the rule, ignoring the implementation. That is, if we're testing the isValid function, we could give an input that contains an invalid operator. We're expecting it to be rejected just by definition of what validity is. If such a test fails, it highlights a gap between my expectation of the rule and my implementation. Additionally, we could also do glass box testing, which is aware of the specific implementation details of the function. For example, while two operators appearing side by side is typically invalid, my code makes a special exception for, say, a negative sign coming after another operator, because that could just mean we're referring to a negative number. Since my code goes out of its way to detect this, one test case should exercise this functionality to ensure that it works as expected. It's really quite cool to run these tests in the browser. The testing libraries will automatically call the functions with the appropriate inputs and show a checkmark if the output produced matches expectations. With this assurance, I can start to make the program bigger while keeping the complexity in check. With the basics in place, I began implementing more functionality, including enforcing which glyphs to exclude and which must appear in the final result. By this time, I already have a workflow laid out well. Implement a feature, then write tests. Make sure it's okay, then move on. As the problem got bigger, I also introduced a second kind of test, the integration test. The kind of tests we've done previously were called unit tests and aim to test small units of code to ensure that they work correctly. The smaller the unit, the better, because there's less complexity under test, and this reduces the risk of us missing things out. Integration tests, on the other hand, go bigger. If you know that the individual units work okay, we want to move on and ensure that when they talk to each other and work together, they're still okay as a system. The integration tests are pretty strict, putting inputs in to generate possibilities as a whole and checking to ensure that the entire set of results produced is as expected. At this point, very satisfied with what I have so far, I tag the commit as a milestone. Just a note to myself that things have gotten to a point where everything is stable, albeit with a limited set of features. Anything I add should build on top of this hopefully nice and solid foundation. This is where I can then move on and begin work on the view and controller, that is the HTML GUI, as well as the relevant JavaScript code that links the GUI with the main logic. Once again, I start small, first by adding basic GUI that only defines the equation itself, watching that work, generating guesses, watching that work again, before turning to bigger features like selecting the must-haves and excluded elements. With GUI, it makes exploratory testing easier, in which I just try out things and see what happens. I even have enough now to actually attempt real games with them. Doing so begins to reveal some interesting bugs which I had not anticipated before. For example, I had not previously eliminated certain operator combinations like having two multiplication or division operators side by side, since I had assumed that the evaluation step would throw an error when they appeared. Turns out there were some edge cases in which that does not happen, so these slip through the cracks and appear in the suggested solutions. I would have never caught that if I didn't actually try to use the program like a user normally would. But now that I've noticed the error, I could go back to the logic page and fix it. Of course, as with my usual habit, I would immediately write test cases after making the fix to ensure this problem would never crop up again. In other words, this is to prevent regressions in the future, in which known bugs resurface. Actually, I should be a little bit careful in talking about code correctness. That's not really what we're trying to do with testing. Instead, what we're really doing is challenging assumptions and managing expectations. Here's one example. Nerdle does accept guesses in which you use zeros to pad out numbers if you don't have enough digits. Fair enough, right? I would also assume that JavaScript accepts this convention as you would in maths. However, turns out, JavaScript has a slightly different way of looking at things. If you have a number with a leading 0, it is taken to be an octal number, that is, a number in base 8. So, if you define a number variable with a leading 0 and then immediately look at it after, its value changes. As someone not expecting this convention, this was really quite counterintuitive. All credit due to JavaScript, if you use its strict mode, it actually raises an error which prevents this from happening silently in the background. But I didn't, which resulted in a bunch of really confusing errors that just looked like bad maths at first. Interestingly, there has also been points in which my code was too strict around certain edge cases. One example here is how I was eliminating possibilities like double negative signs, which I thought weren't okay, but are in fact acceptable by Nerdle. Anyway, it's now time to move into the second phase of development, where more optimization comes into play. There's a lot to be done here, but thanks to the solid foundations we've built at the outset, we have the confidence to do a lot more. I've noticed that with larger integration tests, the unit testing framework even pops out a little timer, showing that certain operations take quite a fair bit of time. Knowing this, I create even larger test cases, with the hopes of using time as a rough benchmark to assess the quality of my optimizations. During this time, I also do a bit of refactoring. This refers to the act of moving code around to improve its organization, all while not changing how it behaves. Again, I hope you're seeing the pattern here. We like to do one thing at a time. If you're reorganizing, don't change functionality. This stops you from breaking too many things at once. In fact, I'm so concerned about breaking things in a nice and controlled manner that I started to use branching to add new features. This is something you can do in revision control to allow 2 or more revisions of the project to coexist simultaneously. Typically, this allows you to create a branch in which you can add potentially breaking new features while also keeping a main stable version around. You can even have multiple concurrent branches, each developing a different feature. At the end of the day, when you're sure it's stable, you could merge these branches back together to have these features populated back into the main master branch. One of the biggest optimizations I've added here was the shortcut solver, a feature that's really quite fundamental. It kicks in whenever we have a complete equation on the left of the equal sign. You don't really have to guess at the digits that come after, do you? Just compute the equation and either it fits the blanks perfectly or you have an incorrect solution on your hands. This cuts down on a ton of needless trial and error. The basic version will only do this if all the spaces at the right of the equal sign are unknown, so if a digit was already filled in, it would fall back to trial and error. Eventually, I relaxed the condition further so that if there were digits already filled in, we would compare the answer against what was already there. I also added other features on the GUI, again in its own branch. One big one was a priority system for potential guesses. This is a heuristic, in other words, a guess at which combinations are more likely or at least more valuable. The top priority tier consists of guesses that contain all unique, no repeated glyphs. This is a great place to start since you'll maximize the amount of feedback you'd get about as many glyphs as possible. The lowest priority tier, on the other hand, consists of all the weird combinations like negative numbers, zero padded numbers, and multiple operators in a row. Again, with each revision, new test cases are added and all test cases are run to ensure that there are no regressions. I even tried some experimental things that never ended up in the final result. Like for example, I read that JavaScript sets were more performant than the arrays I've been using. So I created a branch and in it, I converted every data structure into sets. Unfortunately, that didn't seem to be much of an improvement, so I never merged that back into the main branch. And this brings us to the present. With about 1 week's worth of work, according to Git anyway, the program is complete. This is really just a small-scale project and can really be done without all the software engineering overhead. But it's good to put all of that into practice once in a while. Plus, it allows me to come up with something that I'm quite proud to talk about and even openly share the entire repository for. This has been tested with many days worth of Nerdle questions in various forms, and while there's still a ton more optimizations that can be done, I think I've enjoyed my fair share of this project and it's time to let it out into the wild. If you're interested in studying it further, I've pushed the entire repository onto GitHub. I don't typically use GitHub since I work alone, but I'm excited to see if any of you would want to tinker with it further. If you're not familiar with GitHub and or don't use Git, you can still download the code by clicking on the green button labeled Code, then click Download Zip. If you do use Git, feel free to fork the project and play with it, and I'll even be happy to look over your pull requests if you have any as well, though I can't promise I'll be actively maintaining and updating this project. Who knows, if this gets enough interest, I could even create a follow-up video with more emphasis on Git and collaboration. This of course depends on the pull requests you send in. But for today, let's go ahead and leave things off here. I hope this has allowed you to see some examples of software engineering applied in a real-world context, and through this, hopefully see its value. That's all there is for today's episode. Thank you very much for watching, and until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you liked this video and are feeling generous, a donation to this channel will be greatly appreciated. There's a link on screen and in the video description for more details. Meanwhile, please do like, comment, and subscribe. This helps the channel tremendously and gives me the means to do more. Thank you once again, and I'll see you next time.